So, excuse me. As performance task number 4. So we'll start with question number 1, and we're asking if this reaction we have right here is endothermic or exothermic. So I'm saying that it's exothermic, and the reason I know this is because our enthalpy change, that's denoted by this right here, is negative. So if we look back here, we see that it's negative 2,220 kilojoules, and a negative number indicates the release of energy from the system into its surroundings. If we had a positive number, it would be endothermic, and it would be from the environment or the surroundings into the system. Number 2, so we are going to be using this equation to determine specific heat, or we're using the specific heat equation, and what we're doing first here. Okay, so we're taking our specific heat, we're plugging that in here, so that's 4.18 joules per gram Celsius, and that's the capacity of water. And we know that because we have the mass of H2O, so water is what we're using here. We multiply that by the mass of the water, which is 250 grams, and then we multiply it by the change in temperature of the whole thing, and we've got that down here, 5.8 degrees Celsius. So we multiply all these together, we get 6,061 joules, and we divide that by 1,000 to get kilojoules, right? Because it's a kilo is 1,000. So we end up with 6.061 kilojoules, and that's the amount of energy that's released into the water, right? That's what we saw the change. So then to find the value of propane, we then take this as the amount of energy released, and we divide it by the amount of propane that's burned, which was 0.12 grams. And we end up with a value of 50.5, when we round it, 50.5 kilojoules per gram. Question number 3 is calculate the heat that would be generated if 155 grams of propane combust with unlimited oxygen. So to do this, we first we found the molar mass of propane, so that we could calculate the number of moles of propane. So we take carbon, hydrogen, we take their molar masses, we multiply by the number of atoms that we have of each, and we get this figure, 44.097 grams per mole of propane. And then to find the number of moles, we take 155 grams, which is the value we started with, and we divide it by the grams per mole. And we end up here, after we round it, with 3.515 moles of propane. So then to find the amount of heat, we use kilojoules, we have to multiply the number of moles we have by the number of kilojoules per mole, which we got again on the front sheet as our first value, the change value that we had. So we end up with negative 7,803.5 kilojoules, and we keep that negative number, which supports that it's exothermic. Number 4, we have calculate the moles of carbon dioxide produced in the previous question. So if I hope you can see all that. So we took this equation that we had to show this reaction, and we just compare how many moles of each do we have. So we had 1 mole of propane balanced equation, sorry. In a balanced equation, we have 1 mole of propane and 3 moles of carbon dioxide. So our ratio is 1 to 3. So we take our moles of propane, which we had right here, and then we multiply it by 3 because it's a 1 to 3. And we end up with 10.545, and I rounded it a little bit to 10.55 moles of carbon dioxide that's produced. And then on number 5, so it took a little bit for me to try to figure out which equation to use here, but because we have a constant pressure and this temperature here that we're going to be using the ideal gas law, which is pressure times volume, excuse me, equals nRT. And now I'm totally blanking on what these stand for. I had this written down and now I can't find it. Anyway, we'll move on. So anyway, we're using this equation, and so these are all of our values. N is 10.55 moles of carbon dioxide, which we had from the previous one. Our temperature is 2,253.15 Kelvin, and we take, this temperature of Celsius, we add 273.15, and that's how we get our value in Kelvin. And then this is let me see if I can find it really quickly. Sorry about that. So we ideal gas law based on the value of R, because we have ATM or atmospheres. We're using this equation here because it sells for atmospheres. Sorry about that. Anyway, and then P is pressure, and that's the number of atmospheres that we have, which we took from up here. Anyway, we just plug it all into that equation, and because we're solving for V, we end up taking all of this and we divide it by 1.5 so that we isolate V on this side of the equation. We do these calculations, plug it into the computer, and what we get is 1,858.644894 liters, and I rounded that to 1,858.6 liters of CO2 produced. And then for number 6, the question is, the carbon dioxide produced in the reaction is collected and cooled to room temperature at constant pressure. What's the new volume? So we're using Charles's law here, and that's defined as volume 1 over temperature 1 and volume 2 over temperature 2. So these are all our values. Volume 1, just this answer from before. It's the number of liters that we have, the temperature from before. That's what we've got. And then we have temperature 2, which is this 27 degrees Celsius plus the 273.15 to put it into Kelvin. And then we plug it all in, but because we want to solve for V2, we have to arrange this and get V2 on this side of the equal sign. So we sort of arrange it all like this. This question mark becomes V2. And because we have all these other values, we do 1,858.6 liters multiplied by our 300.15 divided by 2253.15. And that'll give us a value of 247.5906131. And we rounded that to 247.59 liters. And that would be the new volume of the gas. Great, thank you.